I appreciate CPR.
Feeling pretty similar. I knew you weren't dead. You were still talking.
I'm not that much of a talker, believe it or not. You know why? You know why? Because nobody wants to hear it.
What about that time where I said I wasn't going to take much of your time and we ended up talking for like 20 minutes about MST Masters programs?
Yeah, well, that was a productive conversation.
I think you're more of a talker than I think you are.
What?
I think you're more of a talker than you think you are.
Trackers for
You know,
real-time guitar attack.
I work at home as much as I can.
Self-proclaimed fire hose.
Right. As a lecturer, I'm a fire hose. I don't know what to do about it. Well, that's why I pre-record all my lectures. So you can run them at half speed, you can run them at quarter speed, double speed. So
You still need a fireman to hold the hose and
yeah, I just need Chet on the throttle.
yeah, exactly.
That's all I need.
You just need Chet's the fireman, you're the fire hose.
So I'm going to now spew information in your direction about Shazam. So Shazam was started actually in the 90s, believe it or not. It's really way back there. So 3 guys from the Berkeley Business School were sitting in a pub, listening to music, thinking, wow, it sure be nice to know what was going on there. Shouldn't I be able to hold my phone up and just, call some number and then hold up my phone and find out what that is? And they were in the business school. It was their job to come up with interesting business ideas. And so they decided to go off and try to do that. And so they networked around and they found me and they came down here and met with me for a full afternoon. 3 guys, all 3 of them were here for the whole afternoon. And they wanted me to rank all my graduate students, from top to bottom. Who's number 1, who's number 2? And at the top of my list at the time was Avery Wang. And then they went off and got him. And then Avery hired me. And then the 2 of us, I was hired by my former student. And then the 2 of us worked out this algorithm. And but of course, much more has happened since then. I mean, the company has grown, and there's all kinds of things going on. So this is Avery is the CTO, and but in the beginning it was just him and me walking around talking about what would we do, and it'll be very familiar to you because it really is based on what we're talking about. I mean, so this is a spectrogram. You all recognize the spectrogram, and so what are you going to do if the problem is how do you recognize music in a noisy pub? What are you going to do? Right. So first thing you think about is how do you do it, right? So if I'm, if the music's in the next room and there's like 25 people having loud conversations between, I can still hear what song that is. Why? How do I hear that? What is it that you notice? What is it that allows you to identify the song? Well, it's usually just some little segment of the most salient aspect of the music. Maybe it's the lead vocal, maybe it's a little saxophone riff. It's just something that kind of pokes up above the noise, kind of punches through the spectrum of everything else going on. But it may not have much to it, right? It's just a little sliver of what's going on, but it's enough to allow you to identify it. You say, that's, so-and-so singing whatever. So that's what we had to do. And of course, sinusoidal modeling, spectral peak modeling had been around for decades. We've been doing it in many ways. Many dissertations have been cranked out in that area. So we really knew, spectral peak processing and spectral peak tracking. And so it was a very straightforward thing to say, well, we're going to work with the spectral peaks. And so here's a spectrogram. And so the idea is to go through and find all the peaks. So all the little dark spots form the most salient audio. And of course you want to weight this for equal loudness. You want to do an audio spectrogram so that what you see is what you hear, so you have to calibrate everything just right. So you go through, you find all the peaks, and then you get this signature, or you can call it a constellation. And so X marks the peak. So everywhere you see an X, that's where there was a local peak in the spectrogram, a peak that is most likely to survive noise. It's most likely to get through the tire noise in your car or all the people talking in the pub. And so that is then the signature for the music. Now what happens if, okay, I had an idea for a demo. Let's see if I can do part of it. So now let's suppose somebody sends in a little 10-second recording on their cell phone, and you measure it and you find peaks here, 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 here. So it turns out you get this constellation of peaks in the little 10-second sample. So So that then has to be compared to the database. And so all you've got on your cell phone segment is this pattern of spectral peaks. So what you have to do at Shazam Central in London, in the server where you've got 2 million songs in a database, the entire length of the song, on the order of 1 billion peaks, you've got on the order of 1 billion of these X's in your database. You have to take this segment and slide it through every single song in the database until you get a match. And the computer's pretty good at that. The computer can tell when it's lined up, and that's a very powerful signature. And it's actually better than what the human can perceive, because humans don't realize that the timing is so precisely correct. We're really good at saying, okay, the frequencies are exactly right, it's in tune, the chord is in tune, but we're not that good at time comparisons. So, for example, if it's a 10-second segment, noting that this peak is exactly aligned 10 seconds before this peak, that's information that only the computer really can put to work. So the computer can do this better than we can. And so, for one thing, you can recognize many multiple tunes. So you can have 5 songs playing in a noisy pub and recognize all 5 of them in superposition. You'll see 5 big lineups like this in a lot of noise. There'll be statistically significant matches. And it doesn't matter how many other X's there are. If there's a really unlikely overlay, then that's a match. And so you'll get 5 peaks and 5 different songs if they're all there. But the service only really gives you 1 because people don't normally want more than 1 match. Andrew, you're going to say?
Oh, I was just asking if you take this spectrogram over the course of the whole song, but I see how it's working now.
Yeah.
It's quite clear to me.
Yeah. So you have to slide it through. You have to do a match. Ethan.
Why do you need anchors then? So you have the anchors as well as the peaks.
You have read the paper. So Ethan's looking forward. Okay, we'll get there. We'll get there for sure.
So how does it do it? So how does it slide it by all the songs? So
Well, that's the right question, and that's going to get to Ethan's anchor point. So, how would you do it based on what you know right now?
I was just saying it's not that much data to go through because it's just like a XY pairs, and you don't need that many XY pairs.
Yeah, if there are 1 billion peaks.
Yeah, I mean it's a lot, but it makes like the amount of data that's in a song is like vastly more than the amount of data that's represented right here.
Right. We've already got a very sparse representation.
Yeah.
So what you need is a very efficient way to find this alignment out of 1 billion peaks in a database of 2 million songs. How do you do this? How do you find this? How do you search through the full length of every song in the database for the best signature alignment? What would you do? What do we know how to do already? What does it remind you of when I slide that thing through there? Yeah, exactly. So you want to do an autocorrelation. So what it is a 2-dimensional image autocorrelation that we want in principle. And so this autocorrelation value is going to be basically the number of peaks. There's no magnitude information retained, and that's because we're expecting a lot of noise. And so we don't care what the EQ is, we don't care what the compression is. We're just going to, what we care is where the peak is. And that's a summary for a lot of integration under the Fourier transform. So it's a very powerful statistic, so to speak. So, so this would just be like the count of overlapping. You can just think of it as counting up the overlaps. So the autocorrelation here, or not, this is actually a cross correlation. Well, it starts out as a cross correlation, but when it aligns, then it's kind of an autocorrelation where one of the copies of the signal is distorted by noise and the channel and dropouts and even time scaling, because a lot of radio stations will time scale their signals to get them to come out at a certain time. So you'll see up to 10% time warping, which moves them out of tune by 10%, but it helps them program. So in principle, we're doing a cross correlation here and finding the peak. But that's really intensive amount of work, and so you can speed that up. And one of the big things you do in signal processing is find faster way to do things. Okay, so can anybody think of a way to speed this up?
You could, sorry, go ahead. You could, in the database, database, when you're creating these profiles for songs, you could add some kind of metadata, like indicating that if all of the, like if a song is in a certain key, you're gonna get a lot of concentration of loud notes on the time of that key. At least in theory, it's gonna spend a lot of time hitting those notes.
Right.
So if you could group, if you took your sample and just did a quick sort of histogram type thing where you're hitting F a lot, and a lot of the notes in F major, you could run it through just the bits in the database that are tagged as probably F major first. And then if that didn't work, expand to.
You know, that idea might be applicable to the current Shazam database. I don't think they're doing that right now. Well, they might be, because they've been, you know, coming up with new ideas and filing patents for many years. But that's a good idea, and that goes beyond the algorithm that was used originally. So what was used originally was at least, you know, treat these as features that just have a time and a frequency value, and then they're sorted to facilitate searching, like binary searching. But then, to use your idea, those sorted lists could be segmented by key. So you could do a key identification of your submitted sample, or chord identification even, which is pretty reliably doable, and you know, over segments that are tonal. And then you would search that key first. So you would have it grouped in blocks, and you would essentially speed it up by a factor of 12 that way if you restrict to chromatic normal tuning. So I'll mention that to Avery, and if they patent it, we'll cut you in on a royalty. It may have already been done, I don't know.
Yeah.
But it's a good idea, and you're absolutely
You could
right.
also probably do it by amplitude, because basically if you imagine something with a beat
Yep.
at a regularly recurring interval, like this song is at 120 beats per minute, you can
Yes.
group it, like selectively search
Right.
through other samples in the database that are about that tempo.
Yes, and you could classify it as 3/4 versus 4/4. So right, so you could do all kinds of musicological pre-screening and identify metadata, and then have the database organized according to the metadata, so that you only search matching metadata first, and then work your way out to less well matching. And then at some point you might truncate and say, well, if it's not even close, I'm not even going to look. Absolutely, because at some point you do declare no match, and that is, you know, that is my fate. You know, so I help work on this, and almost no music that I care about is ever in the database, because everything I like is so obscure. What they always make sure to have the most common in popular music. So you'll definitely have the Billboard 100 in there for the last 10 years or whatever. So all the oldies and the people really love are going to be in there, and actually more and more classical music is in there. You know, the best Herbert von Karajan recordings in St. Martin of the Fields. All the really good classic recordings are showing up. But if you're into you know, symphonic progressive rock, you're pretty much out of luck. So, but you know, and I you know, have dinner with Avery occasionally, and I twist his arm. But that's all in London. That's all in London. I have no control. So so that's the basic problem, and you get a sense. And so the original algorithm for speeding this up involved anchor points. So let me show you what that looks like. So let's see. I need to find the right. Oh, here it is. So now let's look at this figure, and this shows you. So it's the same constellation, and the idea is you pick a point, and you do this for every point, and so every point gets to be an anchor point. And then when a point is an anchor point, you define a region of influence for that anchor point, and there's some number of peaks in that region, and you can shrink or grow this rectangle to get the number you want. Like 10 is a good number. So, and there's all this analysis to see, you know, exactly how many you want. There's a trade-off going on. So you sort of optimize that trade-off, choose your region size, and get around 10 other peaks associated with this peak. And then what you do is you store the delta t and the delta f. So this triangle here has a delta t and a delta f corresponding to these 2 points. And you do it for every point in the region of influence. So this anchor point generates a list of 10 fingerprints, they're called, which consist of a delta t and a delta f relative to that point. And so that is, so it's going to increase your database size by a factor of 10, but your features are now much more powerful because, if a song, so it's much more likely that a song will have a pitch at A440, a magnitude peak at A440, but it's much less likely that it will be followed at a specific delta T by a specific delta F. So it's a much more powerful indicator or unique signature component. All right.
This also helps for when pieces run at a different time, right? So when through radio broadcasting, maybe a song was shifted 10% of pitch. The ratios between these deltas are going to continue being the same.
Yes. So you can search. So when you search for matches, you can do it with a 10%. You can allow a 10% variance in delta T and a 10% variance in delta F. And in fact, they'll go together, right? So as you shrink in time, you're going to stretch up in frequency. So you kind of really just have a kind of a line search in that two-dimensional zone if you're just searching over time scaling. So that's a nice refinement. All right, so that's the data structure. So all this stuff is just put in a list and it's sorted. So the fingerprints, so there's 1 billion fingerprints in the database that are sorted. And then you sort the ones in your, well, you don't even have to sort the ones in your test thing because you basically are taking each peak and forming the fingerprints, and then you're just trying to find those. And in a sorted list, you just jump. There are all these database techniques for very efficiently sorting a list. You can even have like table lookups. It can be very, very fast to search in a sorted list. But breaking that sorted list into groups according to metadata would speed it up even more. And they're probably doing that, and they probably have patents on it. I'm not keeping up, I'm sorry. But I have a lot of students who are working there over the summer, and they would know, so you could ask. But it may be confidential. But if it's patented, it'll all be in the patent record, so take a look. In this kind of world, it's very standard to get a lot of patents and then never enforce them. That's another cultural discussion we can have sometime. So there they are, and let's see what else. If there's another figure here to talk about. All right, so this is then just one little feature. So it has a particular time and frequency for this anchor point, and then time and frequency for the next point. So you form the delta T, and and you don't form a delta F. You actually use the delta F. So the hash key, so to speak, is the frequency 1 to about 10 bits of resolution, frequency 2, and then the time difference between them. And then there's this second field that's the absolute time, because you do need to know where it is, in the original song. Okay, so now I think I've got another figure. So this shows you an example of what happens when you go through and find all the matching features and plot their. So here's a matching feature corresponding to time, 35 in the database, and time, 4 seconds in the sample that was submitted over a cell phone. And then you do that for all of the features in the cell phone record, and so you get a scatter plot like this for every song. And so for each sound file, you're looking at something like this. So now, if it matches, though, you'll see something more like this. So if when it's the right thing, then there'll be some time in the song that you've stored in your database where the beginning of the recording on the cell phone began. And then as you go through time, you'll get this progressive sequence of matches. And then the slope of this line will tell you how much time scale there is, if there is any time scale. But you'll still get a line if those individual features haven't been stretched too much to actually break the recognition. So this is the kind of thing. So now suppose you've found, let's suppose you've computed this. Yeah. So that's what we now have to notice. So how do we detect that? How do we find that this diagonal line has occurred in the scatter plot of matching hash locations? So we have to, so the location where it begins tells us where the segment started, which we don't really care about. All we really care about is this line exists. It means that the file we're in is the right one, and this is the answer that we're going to send back over the SMS text message. So what if you just rotate it 45 degrees that way? Then you can just look for a peak. And so how do you do a rotation? You can multiply it by a little 2x2 rotation matrix. And if you don't worry about normalization, it's just 1 minus 1, which means you basically just subtract this axis from that axis, and you get a nice, what looks like a histogram. Basically, that's how you would form a histogram. You just rotate that scatter plot 45 degrees, and you get a histogram. And now you can just run through, and now you can just set a threshold. And you can say anything above this value is statistically significant. And you can also just store the peak and go ahead and search your whole database and return the top peak as the answer. And I was mentioning, if you have 5 songs present, you'll get good solid peaks out of all the other songs as well. And so you can report any number of matches, because those signatures are very powerful indicators. So that's basically it. That's all that's happening for the identification stage. And that's how Shazam works. But as I say, there's a lot of new stuff going on. Here's some results on recognition rates and noise. And you see the noise robustness. And that was a requirement from the beginning. These guys were in a pub. It was noisy. And they wanted to know what it was. So this shows you that you get on the order of 100% recognition down to near 0 dB signal to noise ratio. That means that the signal power and the noise power are about equal. 0 dB SNR, signal to noise ratio. So it matters how long the segment is. So this solid line is 15 seconds from the recording. And then this dotted line is only 5 seconds. So you see that 5 seconds is not great. You'd like to at least get up to around 10 seconds to be able to survive a 0 dB signal to noise ratio. And so this gives you a feel for how much power a little more time gives you, and also a feel for just how strongly you can identify things. Now this is additive noise, like hiss. The real noise is more bursty, and it's people talking. Although tire noise is very much like white noise. It's just kind of a shaped white noise. And when you're driving in a car, the dominant noise is tire noise. So close your windows if you're driving and you want better recognition. So the noise really is not important if you have enough sections where the music comes through. And that's usually how it is when you're listening in a crowded environment. You get little snippets of the signal that are undisturbed because there are little gaps in the conversation. And so you just need enough of those gaps to nail it down. And that can happen in 5 seconds or 10 seconds. So that's a feel for the performance. And this is showing the effect of GSM compression, which is used in cell phones, in addition to the noise. GSM is actually looking for voice, so it's a very aggressive compression technique, specifically aimed at voice. And I believe it uses kelp. I'm not sure that's the only thing it uses, but kelp is Cobook excited linear prediction, and that's a specific. It's actually a voice modeling kind of approach. So it's a real drag if you're trying to listen to piano through the cell phone or something like that. But if it's But you do see that you can still do pretty well, but you need signal to noise ratios. You need to spot the signal to noise ratio by an extra 9 dB or something like that.
By any chance, does Shazam that you know of use any sort of, statistical things like, these are the top 100 songs on Billboard right now, check these first? Okay. Because I know sometimes if it's a really popular song, all I've got to do is 2 seconds and it's it's Katy Perry. Try something harder.
Right. Yeah, there's a lot of caching going on for the most common stuff. Mm-hmm. Right, that might actually happen right there on your phone.
How much, when you guys were creating the algorithm, were you guys aware of move over to smartphones and the possibility of that sort of magic thing that happened with smartphones where all the analysis was happening on the phone, the hash table was
Yes. Well, so there's been a long history. both in Shazam and in general for voice recognition, like Siri and the Google Voice. The original situation was everything had to happen on the server, but as the phones got more and more powerful, then we're able to move more and more into the phone. And so nowadays you'll have all the feature formation done in the phone because it's just perfectly fast for that, and you can send back just the fingerprints. And in the case of voice recognition, you'll just send back the kelp coefficients. MFCCs, the mel frequency cepstral coefficients. You actually are ready to know what that is. The cepstrum is just the inverse Fourier transform of the log magnitude spectrum. So it's not that different from the autocorrelation function that we were looking at. I'll say it again. The inverse transform of the power spectrum is the autocorrelation function, right? We just spent a lot of time looking at that. Well, what happens if you take the log?
I think even if you went into MATLAB and computed something on a sample, I think that would be a little bit clearer. The cepstrum is a lot to take in.
Well, not if you think of what I'm just. If you just let me finish this one sentence and tell me if you agree. So you understand the inverse transform of the power spectrum, right? It's the autocorrelation, right? Now, what happens if I just take the log of the power spectrum? All I'm doing is making it more audio friendly, right? It's just more like an audio. I'm just converting it to dB. So I'm making the power spectrum more like an auditory spectrum, right? Well, the inverse transform of that is the cepstrum.
So when you have a spectrum, a lot of times what they'll do is take this signal where this is a linear axis. They'll apply a log function to this to get it to look more like an audio signal. It's kind of like amplitude compression. And then
Yeah, it's more like an auditory magnitude scale in the frequency domain. So you can think of it as the autocorrelation function where in the frequency domain it's been perceptually weighted in a good way. So it has properties very similar to the autocorrelation function, but it's just more auditory friendly. It's just better for audio. And it's become the standard for speech recognition. So voice recognition is based on the MFCC coefficients, mel frequency cepstral. And mel frequency means that the frequency scale is also made into an auditory frequency scale. So the cepstrum means the amplitude has been auditory normalized, and mel means that the frequency scale has been auditory normalized, transformed. And so it's just an auditory version of the autocorrelation function. And it's become the standard feature vector for speech recognition. And so what I was going to say is that the phone does that. The phone will form the MFCCs and send them up to Siri, and Siri will do speech recognition from that. And so it's a much more sparse stream coming out of your phone, and a lot of the work's been done. A lot of the heavy lifting has been done already in your phone. Well, we have 2 or 3 more minutes to wrap up the quarter. So I guess our next meeting is the final exam on Monday.
what time is that again?
12:15 right here on Monday, and we have a review session on Sunday at 2. So really it's my recommendation for how to study for it is just review the homework solutions. Maybe if you feel like you need to read something to understand it. If you don't understand anything, just go reread that section of the book or something. If something in the solutions doesn't make sense, figure out what it's saying, and and it should all be in the book. And of course, ask each other, ask us, because once you understand your homeworks and the assigned reading, you're ready. And you can prepare like a one-page cheat sheet if you want to write down the DFT. Of course, it'll be on the board right here with the wrong sign. But you can write down any formulas. You can write down any number of Fourier theorems.
If I were to change the sign of that on the board, who would change it back?
If what?
If I were to change the sign on the board, who would change it back?
I don't think they would, because it's happened so long ago.
And I'll fix it.
And you could fix it in erasable so that if somebody really has an anal obsession.
I'm fixing it in permanent, because you're the guy teaching most of the signature process classes.
Yeah, anyone who's double E derived is going to like it my way. And, you know, it's only, I don't know, physicists and maybe mathematicians who I don't even know.
Can't reach that.
Yeah, no, this requires a ladder. This was originally written by Dave Berners on a ladder. And I don't know who got up there and asserted the opposite convention, but
That's probably Roman.
no, it happened years ago. It did. It happened years ago.
There's probably some just like student from like 220A from like another department or something, just like, oh, that's not right.
Yeah, yeah.
And erased it and then like promptly left in karma and like didn't study anymore.
And I'm sure it's on video camera. We just have to pull the tapes.
It was me when I was 11.
Before I could integrate.
No, we can change it back. Well, you're the tallest person here, right?
No, you are by far the tallest.
It's true. Oh, yeah. Yep.
You'd be one of
We're
those
up there.
pyramids right now, right?
Yeah,
Give you a boost.
yeah.
Yes, but let's not.
Oh,
So
no, don't worry about it.
again, Sunday, 2 o'clock, review session. I maybe got 20 minutes of junk to say, so bring questions.
It's fantastic.
Office hours for that?
No, no office hours.
No, the review session is instead of office.
If you would like to turn in the lab as late as next Wednesday, that's fine with me though.
After the final exam.
Yes. But before grades?
Before grades. I see what you did there.
Yeah, we're lucky. Having the final Monday means we get to leave early.
Yeah.
You get we get a month break almost.
We get a full,
What? You have more finals, yeah. What?
That's more computer science than
Well, the spectrogram is double E.
But like that's but most of the stuff you did like before should the main stuff like computation.
Well, certainly the database implementation and the log time search for fingerprints. Yeah, most of the implementation is computer science. But the algorithm and the insights grew out of double E and computer music because spectral peak processing is that's a computer music practice. It's not a big practice in double E. It has been adopted in double E and has been adopted in MPEG, but they inherited from computer music. So computer music originated that, it grew out of additive synthesis in computer music. So it's a combination of applied audio signal processing and CS all the way for the database and the search and the fingerprint, the high-speed search algorithms and database management. That's all CS for sure. And I don't even know about most of it. I mean, I had nothing to do with the creation of the database. That was done in London. I never went to London. I was always here. I was always just talking to Avery. Now Avery did go back and forth, and you know I could try to get him in for a talk, get his story on it.
If not, you just give it to
I actually got my so I like a combination of computer music and then I have the music from A and B and B there. And I also have like artificial
What?
I have some like AI practice, so it's like computation,
Yeah, well, if you want to talk through it sometime, that'd be fine. I'd be curious to see what you've got lined up. But ultimately, your choice short, I strongly believe that you should have very strong control over your choices. And the only control we should have is what is the label for that. In other words, you should be able to put together any courses you want to take, and then we can, as advisors, we can help you, fill in any gaps that might be there, and also help label it properly, whether it's joint CSEE or music EE CS, whatever it is. So So that, but I definitely strongly believe that the students should be able to choose their courses.
So I have to like, one of the reasons I have to like add up more like CS classes is like, Maron's my advisor for CS, so.
Who is?
Maron. So he'd also like the chair for like deciding passing the individualized bench facts.
Oh, really?
So like, he would help me a lot with like, lining up the pass. And like, I had to add some like basic like CS undergraduate classes because there were like some CS classes, CS labeled music classes were kind of a lot, but like a lot of them were like electives which weren't considered core CS. So I had to add some like OP classes, HCI classes, and stuff like that. Because like, I framed it as like a music software class, so I would be like doing some programming. I'm like really excited that I got through.
Yeah. So you got 2 more quarters? How much more time are you going to spend on your program? How many more quarters?
I'm a sophomore, so
Oh, so you have another, wow, you have 2 more years. Wow. I'm impressed.
I'm thinking
Yeah, yeah. No, I'm impressed that you're in a class like this as a sophomore. That's pretty impressive, actually.
I was going to take this like remember I was going to sit in.
Yeah,
Because
yeah.
I wasn't sure I was going to get into like career, and then like I'm really like, happy that I decided like taking like because like this class like changed like my career like whole like.
Cool. Well, you know what? We're gonna have a good time over the next 2 years. That'll be well. You'll be state of the art by the time you come out of here.
I'm really like, I'm taking the EE 264 class. I'm thinking of taking next quarter. Like it might be a challenge, but like I'm willing to like put in the time to like. So once I'm done with it, I will have like at least the basics of like signal processing and then.
Yeah. Can you remind me of the title of 263?
264 is the
264.
digital. It's like DSP is the class.
Yeah, and is this taught by Schaefer? Oh, cool. Oh, yeah, that's a must take if you're seriously interested in signal processing. And this is a good course. This is a good prequel to it because it's like this stuff on a higher level. So he wrote the book, the textbook at MIT. Oppenheim and Schaefer. That was the original big textbook in signal processing. Yeah, yeah. It's been used as a text many times. Got something for me to sign?
I might have a version of that book in Spanish.
Really? Wow. Yeah, I bet it's been translated to everything.
Like, don't use right now.
But reading, I don't think it's
Yeah, I think I was like,
so there's a reading committee. I just put the committee from yesterday.
Okay.
I think you need to sign.
I'm up here.
that was actually my sophomore year.
All right, so you got my title, so I just need to sign.
I mean, you can check if I didn't get anything wrong.
This year
Let's see, so what is the date?
I mean, we are on December 4th.
but now I'm I realized I wanted to do more
Okay.
music
For that, and that's my TGR application.
Okay, great. Yep.
He's a friend of mine.
Department
Like
of
my year. Also switched to music.
And so I sign here.
Like 2 years ago, that wasn't a thing. EE music.
And they
And
have,
for the
Since it's new, if you have a good argument
Okay.
for class,
I had to make a form for Jonathan because he's not academic council, but you
like,
don't,
yes,
there's nothing for you to say.
Okay.
Last, you guys didn't mention anything, but
yeah, so it's like
do you want some edits on the proposal, or is that?
Well, I think it's looking good. I don't think it has to be, there's nothing in there that anybody wants to remove necessarily, other than that we want you to focus down on what you're going to really do. Because it's a very, you have a tendency to be very broad and very encompassing. So, but I think you understand that, and nobody asked for changes. Nobody had, we had that one bit of advice for, doing some bottom up.
Yeah, no, but that's.
That was it, really.
No,
Because
but I mean, Devin it's document now for that.
right, so we have to print out the final version and sign it, basically. The final version is, I think we're supposed to sign it, or maybe just I have to sign it. So maybe I just sign the final printout. And I'm ready to sign it, yeah. Because there's nothing about it that I feel is necessary to change, you know what I mean? Because it's kind of a sprawling, rough draft. entry into your thesis area, and we already talked about it quite a bit. So yeah, I'm comfortable signing it as is.
Because these forms can only go in when
With that signed copy, yeah. Yeah, that sounds right. Okay.
So just doing things in order.
Sure. Yeah, no, it's completely fine. You know, we're.
I know the proposal is very broad, and I'm mostly. I think we're opening an entire field. The proposal is just.
Also, it's not binding, right? I mean, your proposal is just where you are right now today. So we all know that it's going to change. I mean, we're going to look much harder at the final dissertation. So, and this could be considered, you know, a starting point on that, right? So you're welcome to keep revising this, and every month you can give us a new version, right? If you want.
Now it's going to be chapters.
Right, it's going to start getting fleshed out, and right. So it's not a bad idea to go ahead and start writing your dissertation. Turn that document into your dissertation.
Yeah. Now we need at least document that we're comfortable now to say this is the proposal as it is.
Right. Yeah. Yeah. We're all 100% excited about what you're working on. We really are. We think it's well chosen, and we think that it really needs to be done. There's not nearly enough work in that area, and so we're enthusiastically behind you on your choices. Well, we look forward to it.
Add some more features on
I
top
think
of it.
there's so many things to figure out. Like, just, I mean, like, I'm just now I'm gonna try to figure out like start like a result, and I think from that it's just gonna be.
Yeah, it's nice to have a series of bottom-up quick results that can make nice little conference papers and kind of fill in a chapter. You know, it's good to have all that in mind.
But now we're just I wanted to spend this quarter like make sure
Planning.
everything has been done.
Yeah, reading and planning. Right. Yeah, that's a necessary step. It really is.
And yeah,
that's kind of why
the like result on the side, like just making sure.
Yeah.
I've got all the ground covered before.
Right. Yeah. In principle, you just have to do that, right? In principle, you have to look at what's out there. That's just basic scholarship, first step.
The dissertation from Yumi, can you tell me where it is?
Oh, we need to ask her. She's around, actually.
Okay.
And she's got the final version coming out this week, actually. I'm supposed to sign it this week. So I haven't seen it yet. But it exists, and we can get it from her. I'm going to get it from her this week. I say this week, I mean next week. Yeah, I'm sure she will. You know, it's going to be published one way or the other. So
The time it goes through, like, I don't know, university things before they.
I'm sure she'll give you a copy. I can't imagine why she wouldn't. Yeah. And she needs to give me a copy.
Yes. Is she submitting tomorrow? Like, because there's a deadline tomorrow.
It's something like, it might be Monday or Tuesday that I'm going to be signing it.
Okay.
So I'm not sure.
I've heard December 5th. I don't know.
Well, she's in a Korean university, so it's not a Stanford schedule. Right. But Jonathan Abel and I are on her committee, even though it's there.
Yeah. I mean, when we get first result, maybe we'll be able to discuss if we want to add anyone in the dissertation reading, or because right now I just put you guys because we're still internal in the project. I don't know if we want to put Zoran or Jens on board at some point, depending where it goes.
Well, I think you want to invite them for specific collaborations.
No,
Yeah. Yeah, so let's talk about that.
Future.
Right. That's something for next quarter, I guess. Although we can think about it over the break.
No, I mean, right now, it's too broad. We can't ask anyone. Until we have we've kind of okay.
Now there needs to be a specific next step research proposal, and we can have a number of things going in parallel, and some of them could be with those guys. And you can get some real help from them. But you don't want to give them your best ideas and not have first credit for what your main stuff is.
It's true.
But you want to be very careful about what you collaborate on versus what you do yourself. You want the main best stuff to be you alone, and then stuff that you think is important and valuable, but you don't mind being a second or third author if it comes to that, then that's what you collaborate on. Kurt Warner's done a good job of figuring that stuff out with the Italian guys. Yeah. Yeah, you can might talk to him. He's really got a good handle on it.
Chatting off and on.
Yeah.
Yeah.
All right. Well, great job yesterday, and you might want to propose a colloque next quarter. You should be. Ramon has been sending out email because that'd be a great way to keep people, including your committee, up to the latest.
What bothered me about chemistry, you're talking about not sharing the ideas and it's public. That's one thing.
It doesn't have to be public.
That's one thing that I regret with those colloquiums, that we don't have kind of a closed equivalent.
It can be defined as private.
Okay.
Right. But it is.
One thing that's bothering me with this.
I see what you're saying. Yeah.
It's been laid out as all the colloquiums open to public and.
Well, you have control over that. So if you announce it publicly, then it's public.
Yes.
But if you don't announce it,
Well,
then
it's common. People still know when it is in shore. That's like, it's at 5 every Wednesday. I don't know. I'm just worried about that.
well, you're right to worry about that if you're going to be getting filing any patents. But what I would argue is that if it has not been publicly announced, if it has not been announced beyond local users, then it's a private laboratory presentation. And presentations within a laboratory are allowed without violating your priority date. So there's an argument.
That's more than the legal thing. It's like just people coming and getting the ideas and then
Right.
getting out.
Right. To be squeaky clean, you have to make sure that everybody present is a member of the Karma community. You may want to check their Stanford IDs if you don't recognize them. Technically, you should, because if you let one random straggler in and he goes off and files, then you really do lose it. Yeah, that's true.
It's not really the spirit we are here. That's why I'm a bit. I don't want to be the guy that counts people at the colloquium. So that's a little bit.
Well, one way to finesse it is to have it in a non-standard place.
Yes, and non-standard time.
What? Non-standard time, right. So seminar room in some random time, and then we'll just shut the door.
But in that case, there could be more DSP seminars.
Right. It could be a special DSP seminar. Yeah, that's a good idea.
That's more. That's what bothers me is that series of colloquiums. It's still you don't want like things that are not really ready to go out too fast.
Yeah, you're right to be thinking about that if there's going to be creative new ideas presented. Literature summaries are perfectly
Sure.
fine.
Oh, well, I could work on that.
Cool.
Okay.
All right, so great job today.
Do you have any criticism? Comments?
Criticism, comments? Well, the main thing I want to say is...
What hat was that? The demo hat. I didn't wear the demo hat.
Oh,
I wore the demo hat before the demo, but I took it off for the actual demo.
Main thing I wanted to say was that, sorry, I went ballistic about the guitars and computer music. I am a guitar player, and I grew up with computer music. I've been around forever, right? And so I